the Janus Point. It's a startling new glimpse into an alternative theory of not only the origin of the universe, but of the origin of the arrow of time itself, suggesting that one of the greatest mysteries in all of physics could be solved with a revolutionary new proposal from Julian Barbour, who's today's guest on Into the Impossible. Come along and experience this journey in what Lise Mollin called a rare combination of humanity and a perspective coming from a lifetime of the study of history and philosophy of cosmology. Julian Barbour writes a book that is both a work of literature and a masterpiece of scientific thought. Come along on this journey into the impossible with me and author Julian Barbour.
Any sufficiently advanced technology is indistinguishable from magic.
Hello, everybody, and welcome to a very special episode of the Into the Impossible podcast, featuring renowned physicist Julian Barbour, who is reaching us all the way from the United Kingdom. And this is Entropy Month and Time Month on the Into the Impossible podcast. We had on Jeremy England, who is not English, but he was on to speak about his book, Every Life is on Fire. And we have Carlo Rovelli, who's written many books on time. And we'll have Craig Callender's wonderful book, who wrote a graphic novel about time. But today we're talking about a very provocative and new theory of time and the origin of our wonderful universe with a real legend. This is such a treat for me. Julian Barbour is joining us. How are you doing today, sir?
Oh, very well, thank you. And for a change, we've got lovely weather here. It's been a very mixed year weather-wise, but it's very pleasant today. I even took a snooze for an hour in the garden.
Oh, that's lovely. Yeah, we are experiencing what is known as June gloom. Even though it's July, we should be frying in July. But in San Diego right now, we've got May gray and June gloom, and it's very disruptive. But we will make it do. You guys deal with it 300 days of the year. We can take a couple of days of the year. Mm-hmm. So I'm just going to read your bio from the book, which you kindly sent to me about 6 months ago, and I keep postponing it because of various activities, and I wanted to give it the depth and attention that it deserved. And Julian Barbour is the author of highly regarded The Discovery of Dynamics and the bestseller End of Time, phenomenal book. He received his PhD in physics from University of Cologne in 1968. He's a past visiting professor in physics at the University of Oxford and lives on the edge of the Cotswolds. I've never been to the Cotswolds. I hear it's lovely, and I'd love to see your garden someday. And we're going to talk about life and the universe and time. But before we do that, Julian, you're so gracious. I want to do what I do with all of my guests who write books, and that's to do what you're told never to do, which is to judge a book by its cover. But what else do you have to judge a book by when you see it for the first time, unless you know the author? I want to ask you, how did you come up with the title and the cover design of this wonderful new book?
I didn't. I came up with the title, and that will come out in our discussion, I think. The cover is entirely the work of Basic Books, and the UK edition. Perhaps I can show you the UK edition, which is also quite striking.
Yes.
There's the cover of the UK edition.
Oh, wow.
And there's the back of it. Roger Penrose saw that cover and said he thought it was a very clever cover.
Yes. So, Roger,
both publishers have done me proud, no question of it.
Yes, it is a lovely work, and it's a work of art as well. And I recognize many names in here, including T.J. Kelleher, who I guess was your editor, or one of your editors. I've known him for several years myself. But I wanted to begin by discussing the notion of time and where does it come from? Because I've had on Carlo Rovelli, I've had on many Frank Wilczek, and I always have these solipsistic or tautological definitions that I am forced to use, such as time is what clocks measure, according to Frank. Time is what increases entropy or is associated with the increase of entropy, according to Carlo, Clausius, and others. What does time mean to you? What is time fundamental? Is time emergent? And what do those two terms mean in the context of time?
Well, I've been thinking about time now for close on 60 years, and my ideas have been evolving, I have to say. But I certainly started off quite by chance in the autumn of 1963 quite by chance, I read an article about what Dirac had said about the structure of Einstein's great theory of general relativity, in which he questioned whether four-dimensional symmetry was a fundamental feature of the physical world. And sometime after I read that, I said, well, if Dirac is saying that, shouldn't we start thinking about what time is? And then I very soon came to the conclusion that if nothing changed, we couldn't say that time passed. So the primary thing is change. What Mach said was, it's utterly impossible to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive from the changes of things. And also in Mach, it was from Mach I learned the insistence he had on the relativity of motion or position, that you define position relative to other objects. And really, ever since then, I've been thinking, my question has been, what is time? What is motion? And I'm still working on that. And I've got a wonderful group of collaborators now. Some are in their early 20s. Then I've got some in their 40s and another very good mathematician who's about 60, I guess. So it's actually speeding up now, these things. Let me make one comment, though, about Einstein, if I may.
Of course.
When Ernst Mach died in 1916, Einstein wrote a very handsome obituary of him. And among other things, he quoted that passage about time that I've just given and described it as a gem. But if you look through all of his works, everything he did and what he wrote, I don't think you'll find any attempt by Einstein to put that into reality in his work.
Wow.
And when he was asked what is time, I think his answer was very much like what Frank Wilczek said: it's what a clock tells. But he didn't. But then, which I think is very significant, in his autobiographical notes in 1948, he said when he'd created general relativity, he'd committed a sin in that he'd introduced two quite distinct things. One was the space-time manifold with the metric on it. And then completely independently, he admitted that he was bringing in from outside rods and clocks that measured it. And he said, that's inconsistent. The rods and the clocks should emerge out of the fundamental equations of the theory. And he never did that. But in fact, I think one of the things in chapter 7 of my book, I do explain how, at least within Einstein's theory, rods and clocks do emerge. And that indicates strongly that they don't exist near the Big Bang. So I think we have to rethink very radically how we think about the conditions at the Big Bang, because there aren't any rods and clocks there.
Right. And I'm wondering if there's anything there, or equivalently at the singularity of a black hole. I want to start maybe even more proximate to that point in time, if it is indeed even a point, with a question I've posed to all of my guests, including Sir Roger after he won his Nobel Prize. And that was, whether or not singularities should be taken seriously, because we know of no process in nature that is infinite, that has unbounded size, magnitude, density, temperature, energy, infinitesimal length scale, et cetera, et cetera. And yet we talk about things like singularities. Somebody said, a singularity, a black hole is where God is dividing by zero or something like that. But we don't really know the correspondence of things that are infinite, but we do know things that are zero. And I want to ask you first, you make a large discussion of what you call the royal zero. Is that somehow going to play a role in a new conception of how we should think about singularities? How does the royal zero figure in? It's the most unique number because it's a number that is scale free. It doesn't need a rod, as you say. It doesn't need a clock, as you say. There's something special about zero. What role does it play in the Janus Point concept?
Well, we would really have to go into where the title of the Janus Point comes from. So this goes back to the first qualitative result in dynamics discovered by Lagrange in 1772, when he was studying the three-body problem that gave Newton such terrible headaches, the Earth, Sun, and the Moon. And what he showed was that if the energy of the system is not negative, so it's either zero or positive, then in the distant past, the size of the system is infinitely great. It comes down to a finite value, and then it rises up again to an infinite value in the future. That's in the standard sort of Newtonian idea of time going from past to future, but you could reverse it because time reversal symmetry. And that point of zero size in the Newtonian representation is what I call the royal zero. But basically, I would say, when I went to study mathematics at Cambridge, they said, what does the equal sign in an equation mean? It means that the two things on the two sides of that equal sign are exactly the same. It's equality. So in some senses, it's saying that there's identity. Now, in fact, I would say rather more than the size, I now think shape is the really fundamental thing. And one should think more about, in fact, I would even say that size is a gauge degree of freedom. It's something we've put into physics which shouldn't be there. So I'm going to start with my famous triangles. I'm always illustrating things with triangles. So if I had just 3 points, three bodies in the universe, and they're at the apex of the three vertices of the triangle, it's meaningless to say what the size of the triangle is because there's nothing outside the triangle to measure its size. So all you can speak about is the ratio of the lengths of the sides or the angles. And if you think about it, we don't see lengths, we see angles. Because when we look at the sky, when we look at Orion's belt, we see that it subtends about a few degrees, but that's a fraction of 4 pi the whole way around the sky. And I think it probably should be 2 pi, shouldn't it? 4 pi is the area. So the thing that I'm saying is that if you just look at what the shape does, I suspect there are no singularities at all. And
is that a fundamental aspect of an error or problem in relativity or in our concept? Because as I know, and I want to talk about artificial intelligence, the problem, Julian, is that I have about 10 hours worth of questions to ask you, and I only have about an hour and a half scheduled with you. So we'll try to be brief, but we'll also try to come back to it. But I don't know that infinities should be taken as seriously as they are, and yet they're sort of treated as sacrosanct in physics. And we talk about the Big Bang singularity. We talk about a black hole's singularity. These are unobservable, and we'll get into falsification later on. But this notion that something infinite can go to become something finite has kind of been resolved or at least addressed since the time of Zeno and his famous paradox. So what extent is if infinity? If zero is real, I guess the question would be 1 over infinity. Why is that not real?
Well,
or 1 over 0. So
yeah. One of the problems I'm facing in talking with you now, Brian, is that my thoughts have developed quite a lot because writing that book was tremendously stimulating. And you may have noticed that at the end of chapter 8, I hazarded a new idea about what time is. So let me to help me get into it, let me talk about these very remarkable solutions in Newton's theory, because I think they illustrate how perhaps cosmology, the way we think about the Big Bang, should be completely changed. Now, in Newtonian theory, it's been known for over 100 years that if you have point particles interacting in accordance with Newton's laws, it is possible that they collide all together at their common center of mass. And this is called a total collision. And in the three-body problem, whatever the masses of those particles, they can either do it on a line, and that was discovered by Euler, or they can do it when they collide together, the shape must tend to be an equilateral triangle. Now, if you say that the size has no meaning, it's a gauge degree of freedom, then if the shape stays sensible and even becomes very sensible and uniform and becomes an equilateral triangle when they all collide, that if you say that the only physical degrees of freedom are the ones that describe the shape, the angles, if they stay well behaved, there's no singularity. So let me hold up this triangle and move it ever further away from the camera. You see the size change, but not the shape. This, to me, suggests very strongly that the shape is the only thing that counts. And this puts a completely different way, potentially, on thinking about the singularities at the Big Bang. I won't hazard anything about black holes because I'm more interested and I haven't really thought much about black holes, but I certainly have about the Big Bang. And I think that's a very interesting possibility. And if you have lots of particles, there are many, many possibilities for these total collisions or total explosions. If you reverse them the other way, then you get a Newtonian Big Bang. And in that case, you can start off one of these total explosions, these Newtonian Big Bangs, where the universe is in its most uniform shape that it can possibly have. And it has the shape of what is called a central configuration. It's a scale invariant quantity. You blow it up as much as you like, but the ratios between the particles just stays the same. And basically, if you think about the history of the universe, let's just forget about inflation. What we know as a fact is that a split second after the Big Bang, the universe was extraordinarily uniform, and it has got more structured, inhomogeneous ever since. And I would think maybe these Newtonian Big Bangs are a model of the universe if you shall we say you put on spectacles and all you can see is the shape and not the size. Of course, we can't avoid putting in a shape as well. I think the reason why we always imagine there's always a size to something is because of the image that's projected onto our retina. And that is the size of the object is the fraction of the area compared with our complete retina. And that's just the same if you think about looking at the sky at Orion, the nebula of Orion, the constellation of Orion. It has a certain size relative to the total area of the sky. So I think the bedrock of physics should be ratios, and at all stages it should be ratios. And if we're talking about a triangle representing the complete universe, it should just be the ratios of the sides or the angles.
Yes, and that brings up a concept that one of my listeners was eager to discuss with you, is whether or not, if time is emergent, and space-time are somehow equivalent, that, shouldn't space be emergent in some sense? And Lee Smolin, our mutual friend, who you kindly asked a question of when he appeared on the podcast about 2 months ago, sad to say he has not reciprocated yet. I'll be waiting. I'll ping him again and see if he can give us a comment, but he's quite busy. But, he kind of has this belief, as I understand it, that, that space-time itself can emerge from basically fundamental constraints on causality. And so what about space would be privileged? In other words, would space pre-exist time?
All science starts with certain hypotheses, and mine is that geometry is fundamental. And actually, my favorite saying is one of Galileo's: "He that attempts natural philosophy without geometry is lost."
That's a great quote.
It's a wonderful saying, and I just don't think you can do without geometry. In fact, I would retain the continuum and all I would retain is angles.
Mm-hmm.
And this is actually when you try, I mean, if you set about taking out everything in the way we think about physics and do physics and say, what redundant things can I take out and get down to what, if I go any further, I will destroy everything and I can no longer walk because I've chopped off my legs.
Mm-hmm.
What I want to know is what is the essential things. And my belief is that it is actually geometrical relationships.
Mm.
And they can be illustrated in the first place, I think, with particles in space. You can do an incredible amount with particles in space, with where you have separations between the particles, and some separations are greater than others, but the ratio is well defined. It's a pure number. That's another of my fundamental principles. The whole of cosmology and physics should be expressed in terms of pure numbers. Now, you can say the rot set in with Newton when he introduced time and distance. So the Greeks always said ratios must be of the same things. So you can take the ratios of two lengths, and then you've got a pure number. But Newton introduced time as well as length in his things. So the velocity is a distance divided by time, dx by dt. And that's an improper ratio. So I want to build up what I call shape dynamics using only ratios of really, I would say, of lengths. That's all I think you need. You could probably just get by, or you can get a very long way with a very interesting theory just using points in Euclidean space.
Mm. And another controversial statement that you make in the Janus Point is that momentum should not be treated as equal to position. This, if true and if accepted, would upend our notion of everything from classical Hamiltonian dynamics to the quantal dynamics that are predicated on such kinds of conjugation relationships. So I want to ask you, what has been the reaction to that statement? That is a very provocative statement, and you admit as such in the book that your courage is undaunted by the arrows that you might take. But maybe they won't do any damage because they only carry momentum after all, and momentum is not real. So, what do you mean by this? That momentum should be kind of treated with a lower priority, perhaps, than position?
Well, let me say first of all, there is a mathematical way of dealing with a phase space which has an odd number of dimensions. It's called, I think, a contact structure.
Mm.
So there is a mathematical way of dealing with these things. And I think the whole problem with this is that people haven't taken Mach's ideas seriously, that really what happens locally is somehow or other is governed by the whole universe. So Mach conjectured that the local inertial frame of reference in which Newton's laws are formulated is determined by the whole universe, by the masses in the whole universe. Mm-hmm. And when you do that, time really in that classical picture, before we attempt to get to quantum mechanics, time in that classical picture is just somehow an average of how all of the quantities all of the separations have changed. So you can have a separation of all of the things. So just put out objects on the table and move them all a little bit. Then each of them will have moved a certain amount relative to all the others. But the totality will make a sort of a background quantity. And then each of them will have a proportion of how much it's moved compared with the others. So you can always ascribe to an individual particle what proportion of the change of the universe it has done compared with all the others. So its momentum is a fraction of all the others. So that's again coming back to the ratio. So I would say in classical mechanics, if you really want to have something that locally looks like a momentum, you've got to say it's the measure of how much it has changed its position compared with how much all the others have changed their relative positions.
I see. So, right. And so that then takes us back to this ratio or gauge-free description. But I also think, Julian, I often say, mathematics is highly abstract in that you've never seen a triangle. We can only visualize a triangle. I always say, if somebody says, no, triangles are real, I say, what does a triangle weigh? And that's a nonsensical question, because triangles are, collections of three non-collinear, connected points, which are themselves of zero dimension, which is kind of mind-boggling for humans to envision. So it's curious to me that you can build up shape dynamics and the reality of dynamics and even concepts like the Janus point from something that's purely imaginary that you would have to admit doesn't exist in reality. I mean, you can't hand me a triangle. You can ask me to visualize it, but can a computer really handle it? No, because a computer has only an approximation at quantized level to approximate a point as 1 over the largest number in its memory bank, right? So to what extent can we build up reality on things that are purely fictional or created by the human mind, perhaps?
Well, two comments about that. First of all, I think all of the great concepts in mathematics are suggested by our experience, and they're idealized from that. And I think the real numbers are a human creation, but I would say let us work with them. Now, I had a few years ago, I had a discussion with Gerhard Toft, the Nobel Prize winner. I've met him a few times. And we had actually about an hour-long discussion. And he was telling me about his ideas. His ideal is to build up everything from zero and the positive integers, nothing else, he said. So I said, you're then like Dedekind, who said, God created the integers and the rest is the work of man.
Menschenwerk.
So then I said, yes. So then I said, yes. But why don't you accept the real numbers? Because the real numbers are a creation of man. Man is part of nature. And he smiled, and I think he accepted that was not an unreasonable point of view. So we have to start with somewhere. And I think there's a wonderful saying of Popper, the philosopher, about there is no really sound empirical foundation of what we do in theory. We just drive down piles into the swamp until they make a reasonably secure platform, and we work on that until we have to drive the piles further down. So that's very much my attitude. So I will happily, for the moment, accept the real numbers and Euclidean and Riemannian geometry. And let's see how far we get with that.
Now, a new concept, for me at least, you may have written about it elsewhere, is this concept of Entaxy. Can you explain that and how that is an improvement, because it must be an improvement upon what we think about as entropy and the ability for systems to convert energy into labor or work, et cetera. So what is Entaxy? What does it do for us that entropy does not do?
Well, let me go back a bit into the essence of the book. I mean, a major part of the book. Thermodynamics and statistical mechanics was born out of the study of steam engines. This absolutely wonderful book that Sadi Carnot published in 1824. His aim was to make a steam engine with maximal efficiency. What was the maximal efficiency that could be obtained? And the key thing about steam engines is the steam has to stay in the cylinder, essentially in a box. Now, you read any of the papers of Clausius, who first formulated the second law of thermodynamics, of Maxwell, of Boltzmann, even up to Willard Gibbs, they all start off by saying, we imagine things like billiard balls or atoms or molecules that are bouncing off each other, but they are in a box and they bounce elastically off the walls of the box. And the whole of statistical mechanics is based on this concept of a box. And Clausius's wonderful definition of entropy in the second law, that requires very careful reversible passages from one equilibrium state to another in a box. It's absolutely crucial. He couldn't have defined entropy without that box. And I have read quite a lot of the literature on the problem of the origin of the arrow of time, what entropy is, and so forth. And I have not seen one single place where anybody has said, does it make a difference if the box isn't there? It's quite extraordinary. But when you start thinking about trying to define entropy when the box isn't there, you're in a completely different ballpark. If you say that the energy of the universe is conserved, and I think that's a reasonable assumption, then you can't do all of the wonderful things you can do in thermodynamics and statistical mechanics, is change the entropy by compressing the box and things like that. So you've got to look for some other quantity which defines a state function. So the key state function in statistical mechanics is the energy. And then you count how many microstates there are for a given energy. And that's not that much difference when you've got a quantum system. You count in a given interval of energies, how many quantum states there are in that interval. But in all of those cases, you've got some system which is either in a box or it's self-confined. So what do you do if you've got a system which can expand freely, like we think the universe is doing? So there is a quantity, which I call the complexity, which is an extraordinarily interesting quantity. It's the ratio of the mean square length of all the separations between the particles divided by the mean harmonic length. So essentially, you take the average of the long distances in the numerator, and then you take the average of the short distances in the denominator, and that gives you what I call the complexity. And it's a measure of how clustered a system of particles is. It's also very remarkably the Newton gravitational potential made scale invariant by multiplying by the center of mass moment of inertia, which is half the trace of the inertia tensor. And this is a very, very interesting quantity. And it is something, you can call it the intrinsic size of that universe of those particles. So we've got a finite number of particles because the distances between the small particles, you can regard them as little rulers, which are measuring the whole size. So if I come to my triangle again, I can take its shortest side and use it as a ruler to measure the longest one. So the triangle has its own size. It has an intrinsic size. And that same thing, I think, could actually serve as a notion of time. And all of this would be in terms of pure numbers. And that complexity in the Newtonian classical theory, when you go from that Janus point of mind, or from a total explosion, that complexity in the classical Newtonian theory fluctuates, but it grows. And that's what I call a state function which grows. And then if you look in these Janus point solutions, you find that the number of microstates in the volume of what I call shape space actually decreases. It does not increase. So I define a quantity which I call Entaxy. Well, it was coined by my collaborator Flavio Mercati, which behaves in exactly the opposite way to entropy. So when you take the box away, everything is turned upside down. You have to, as Kepler said in a different context, we must philosophize about these things differently. And so that complexity goes on increasing forever in a Newtonian system which is unbounded. And as it does that, the universe does not get more disordered, it gets more ordered. Because you find that Kepler pairs form. For example, Kepler pairs form. And when a Kepler pair forms, I'm going back to when Einstein didn't say what a clock is. when you're at that Janus point, the particles are uniformly distributed and they're moving more or less randomly with respect to each other. But then in both directions away from the Janus point, the particles cluster, and very often they will form Kepler pairs. And as that Kepler pair forms, its rotation period becomes the period of a clock, its major axis becomes a rod, and the direction of the major axis becomes a compass. So you've got a Kepler pair, which is a rod, clock, and compass all in one. And relative to it, you can see that the other particles, if they're single particles, are moving in accordance with Newton's first law. So this is actually exactly showing what Einstein wanted to understand. Where do inertial frames of reference come from? And what are rods and clocks? They emerge out of a dynamics. And this can all be done with systems which have zero energy and zero angular momentum, which is what a Machian treatment of a universe requires. Everything falls together into place beautifully.
Wonderful. So the next topic I want to talk about is the notion of a cyclic universe or a cycling universe, a collapsing universe. These are literally as old as time, much older than the Big Bang concept, dating back to Egyptian cosmogenes and other concepts, which date thousands of years before the Common Era. I want to ask you, the classical objection, if I tell a normal person on the street who happens to have an advanced degree in general relativity, if I say, I'm talking with a renowned scientist today about his theory that predicts that time can go in two directions at a single point in the universe's life cycle, they'll say, well, Tommy Gold explored these back in the 50s, 60s, and 70s and ruled them out in some sense, or they were ruled out because of the problem of dissipation of entropy and the unbounded nature that every cycle in the universe would compile more and more entropy. Does the Janus point share anything in common with the cyclical, bouncing aeon? Does it have anything in common, or is it fundamentally different from those conceptions of cosmogenesis?
I would say it's fundamentally different. And I would say the main significance of that Janus point idea, which I'm increasingly thinking serves its main purpose, is to undermine the idea that the arrow of time is due to increase of entropy, and also to undermine the idea that you have to impose some special condition in the past, a past hypothesis, as David Albert calls it, yes, to explain the growth of entropy. So when I showed that example of how the three-body problem behaves, and it's exactly the same however many particles you have, that is nothing whatever, that special point, that special Janus point, is not there because of some extra condition that I've had to put in on top of Newton's laws. It's a direct consequence of Newton's laws. Virtually, certainly, every solution that doesn't have negative energy has that behavior, and moreover, as you go away from the Janus point, the universe gets more clustered in both directions. There's a precise way to characterize that clustering by a pure number, and those defines directions of time. Those are arrows of time that are nothing whatever to do with statistical arguments. It's nothing whatever to do with lots of microstates being bundled up together so that you can't see what's happening. And it's just, I think one of the main things I feel really confident about what I put in the Janus point is that it undermines the standard story about the arrow of time needing some special condition in the past, and moreover that increase of entropy is what's going on in the universe. I argue that what is going on in the universe is increase of structure. It's getting more interesting. And if you just look at me now as I'm pontificating, Brian, compared with what the universe was like just after the Big Bang, I think I've got a point. It's got a lot more interesting and a lot more structured. And maybe people are just blind to this. I think one of the reasons, so the point about thermodynamics, it seemed to rest on such wonderfully secure foundations, the impossibility of making perpetual motion machines.
Mm-hmm.
But it's still, all of its concrete results, all of the solid results rely on that box. You read Willard Gibbs's great book published just before he died. He essentially he's talking about a Hamiltonian dynamics, and the system must have, the phase space of the system must have a bounded measure. That's essentially putting a box in. Mm-hmm. And if you take that away, it's just everything is different. But then I think now increasingly I'm coming to think that much more interesting than the Janus point solutions is the ones where it's really, so that's when in the Newtonian representation the size remains finite at the Janus point. But if you have these total explosions which come out of, in the Newtonian picture, out of zero size, and if you take out the size story, it comes out of the most uniform shape that the universe can have. I think that's much more interesting, but it still defines an arrow of time. The arrow of time is just the universe is going from being extraordinarily uniform to getting ever more varied. And that's actually what, you look around at the universe and the evidence from what the astronomers find, and this wonderful telescope I think you're involved with, well, all of those ones down in Chile, just look, take what they look like. Yeah. It's the heavens proclaim the glory of God or something. They proclaim my idea that the universe is more interesting.
So let's discuss what have been called the theoretical virtues by Michael Keyes, no relationship to me, but he has a paper called Systematizing the Theoretical Virtues, and he talks about what makes a good theory and what differentiates it from an inadequate or a subpar theory. And it goes a lot deeper than the Popperian falsification rubric. It's much more thorough. He does involve certain things that I find controversial, such as your theory should strike scientists as beautiful, as that's a virtue. As your countryman Paul Dirac said, it is more important to have beauty in one's equations than to have them fit experiment. I wish I was with, as an experimentalist, I take personal umbrage at that statement. I don't believe it. I also don't believe that experiments should be held up as the sine qua non of whether a theory should be at least grappled with. And I use the example lately of Maxwell in 1860s when he was coming up with the unified theory of electromagnetism and his famous equations. He wanted a mental model which, if employed and taken seriously, would have led to the falsification of his ideas, because he believed in vortices and gears and ether and all sorts of things. So imagine if Karl Popper were around back then. Oh, no, there's no little gears, there's no little whirls and vortices, so your theory must be wrong. No, so that's not fair. And to be fair to Popper, he said things like he appreciated the steady state and he appreciated other models staying around longer perhaps than history might judge them to be valid, because it impels people to make observations and you want to crack the test. Some of the other theoretical virtues I want to confront you with, and you mentioned observation, and we're going to get to that. The first one of the virtues is explanatory depth. Your theory should apply to a wide range of scenarios if it is correct. It should also explain data. And the final kind of virtue that I'm going to talk about is adequacy. Your theory posits causes that account for the effects of the data. And of course, that relies on evidentiary data being available. So I want to ask you, what are the observable or evidentiary consequences of the Janus point scenario, whether or not, regardless of whether or not we can currently detect them, as you say?
Well, it certainly it says that there will be an arrow of time, a very profound one, that it'll be inescapable. It will be, the dominant feature of existence in the universe will be that we will be aware of an arrow of time. So I think that's a good start.
Mm-hmm. And when we look at data in the universe, of course, we want to be cognizant that that could also be applicable to the past hypothesis, which actually by fiat, which we physicists, find abhorrent, but nevertheless, you could also say that that hypothesis gives us an arrow of time. It doesn't give us 2 hours of time. And so my question to you is, are there pieces of evidence now respecting Popper that could disprove that? Because obviously it's consistent. If I was putting on a critic's hat, I would say, well, that's a retrodiction, Julian. You're trying to come up with a theory that provides an hour of time, but what new, what can we tell my future grad students and your grandchildren, et cetera? What can they look forward to doing to providing evidence or falsification of that scenario, given that we all believe there is an hour of time that we experience? Is there another, is there a consequence of the data? Some limit on black hole masses, some limit on minimum number of generations of leptons. Is there some piece of data, of evidence that could substantiate it beyond the retrodictive nature of the existence of an arrow of time?
The best hope I have is not for those Janus Point ones where there's two sides, but where I have these total explosion ones where in the Newtonian picture it starts with zero size, but the way I think about it, it starts in its most uniform shape. And I think this is where we have the best chance of really making some progress, because if this idea is right, I think it should provide a clear alternative to inflation that at some stage should be testable, because it would show up in the CMB, in the data in the CMB. Because what is out of that theory, all that we've got at the moment is the Newtonian theory, but we can see a good chance that something like it will happen in general relativity, that we're using that Newtonian model of a total explosion starting with great uniformity to try and get some idea of what might happen in general relativity, because there's great uncertainty about the Big Bang at the moment. And in a paper by my collaborators, Kozlowski, McCarty, and David Sloan, they make the first progress to showing that something similar like that can be expected in general relativity. It's related to the BKL scenario when it's quiescent, if you're familiar with that, Brian. So, the great triumph of inflation was to give these fluctuations, the Harrison-Zeldovich fluctuations, out of which then all of structure in the universe developed. And the key thing about the early universe was that it was very uniform, but there were small fluctuations with a very definite structure, the scale invariant spectrum. And the reason why we've come, my collaborators and I, to this picture of this total explosion in the Newtonian theory was a challenge by a cosmologist at Oxford, Pedro Ferreira, to see if in Newtonian theory we could find hints of an alternative to inflation. Because inflation has its triumphs and they're well deserved, but it's very difficult to see how it gets started. And my understanding is there's some uncertainty about how it ends and whether there's internal inflation and things like that. Now, if these ideas are right, if and when we get to applying them to general relativity, I would suggest there will be absolutely no shadow of doubt how the universe starts, and it should make very precise predictions that could be verified in the CMB. And so there's definitely hope there. And it would surely be, I think you have to admit, for all the triumphs of inflation, it's a bit shaky on its foundations. There's a lot of argument about how you get from this very symmetric Bunch-Davis vacuum to astronomers actually seeing a real universe which breaks the symmetry. There's a lot of question marks over inflation. Now, and it's a big if, of course, and it may be decades. If we're on the right track, I think it could be decades before we're vindicated. But if we do come to vindication, it will be a clean sweep. We will start with a very uniform universe. Of necessity, it will start very uniform, and then it will get more varied in a very definite way. And that would be, of course, quite a nice triumph.
Indeed, yeah. I think of inflation more as a theory of structure formation than a theory of the initial conditions of the universe, and that avoids having to think about both its lacunae in terms of inability to explain itself without the existence of the multiverse, which I find personally more to the unpalatable side, as my viewers will undoubtedly recognize, and sort of almost tantamount for a replacement of a godlike fiat instantiation of the universe with an infinite number of creative forces like mini bubble universes. But nevertheless, it is very successful, and one of the things it does predict is that there should be a stochastic background of primordial tensor perturbations or gravitational waves, which are obviously one of the key targets for experiments such as our Simons Observatory and other projects around the world. And the hope is that these could be measured, and that would somehow lead to confirmation of inflation, although which inflationary model and which multiverse kind of scenario, that is not specified. But it makes a concrete prediction. It may not be observable. The waves may be too feeble to leave an imprint. The inflation may have occurred at a low enough energy scale that even though it did occur, it won't produce anything that we could see. Nevertheless, in the Janus point, I assume there are no gravitational primordial tensor perturbations.
In the Newtonian model, certainly not. That's for sure. There may well be in general relativity, but there are really a lot of work has got to be done on the general relativity side of this to really begin to make progress. But I think it is definitely possible there could be gravitational waves, and as opposed to the present situation where a magnitude is unknown, it's the R parameter, isn't it? This should make a definite prediction, I think. But this would require understanding of all the forces of nature. I mean, there is talk of this new fifth force. I mean, it probably would be a complete package, but there's hope. There's hope. Mm-hmm. And all I will say is it's a completely different way of thinking about these things. And it's a very simple one. It's just a very clear, straightforward idea to say that if the universe is spatially closed, there's nothing outside it, then you shouldn't talk about the scale of the universe, and everything should be expressed in terms of ratios. I don't think you can have a simpler, more secure foundation for conceptualizing about the universe than that. And on that basis, once you do that, things change dramatically. Let me go back to Kepler. So when Kepler thought about the observations of the comet that Tycho Brahe had made, he thought that implied that the comet must have gone clean through the crystal spheres that carried the planets. Mm-hmm. So nothing was carrying the planets. And he said, henceforth, the planets must find their way through the void like the birds through the air. We must philosophize about these things differently. So I see this claim that get rid of size. It's a bogeyman. It's potentially causing all these problems with singularities and things. And if you stop and think about it, if I may say so, it's blindingly obvious. At least it should be questioned at the most fundamental level. I think I will go as far as saying it stinks.
So one concept that's gotten a lot of attention lately, and even I spoke with a gentleman, Dr. Stephen Meyer, who supports intelligent design, and we had a lively debate about that. But nevertheless, was this Borde-Guth-Vilenkin theorem that posits that any expanding space-time had necessarily a beginning or ultimate boundary, sometimes misidentified, according to Vilenkin, as a singularity, but more properly, I think, identified by Carroll and others, including Vilenkin afterwards, as sort of the breakdown of classical general relativity. So one of the virtues, I think, of your scenario is that it doesn't require quantum mechanics to be reconciled with gravity. And I always say that until you hand me a letter from God and it says you have to marry, there has to be a quantum description of relativity with that's commensurate with all of our other classical and quantum theories of electromagnetism and quantum electrodynamics. The only two regions where it seems to be relevant are near singularities, which are unobservable. So we have this kind of Ouroboros, the snake eating its tail, that we need quantum gravity to explain singularities, but singularities only exist in regions that are in practice and in principle unobservable. So I wonder if you can take the other side, Julian. Do you think, argue against your position? In other words, a steel man. What do you think are the best arguments that we need, that we have to have a theory of quantum gravity? Do you think there are arguments to be made that support the necessity of a quantum theory of gravity, or is it just kind of part of the appeal that human beings have to make everything classical quantum?
What I feel definitely is we have to have a quantum theory of the whole universe, because otherwise, the facts of quantum mechanics around us. You and I couldn't be talking like this if it weren't for quantum mechanics. That's
yes,
absolutely clear. What I do, everybody thinks. I think virtually everybody in the field thinks that the problems of quantum gravity are at their most extreme at the Big Bang and also in black holes. And for a long time now, my collaborators and I have been saying, no, quantum gravity will, the quantum theory of the universe will take its simplest form at the Big Bang, because there its shape is at its most uniform. And the quantum issues will become interesting later on. And we know they're damnably interesting now, and they seem to be interesting in the evidence from black holes is that they're interesting by then. With the work of Bekenstein and Hawking. So that's how I would put it. And well, that's all I can say. I think that we're looking to turn this upside down. There's an interesting thing. I know Carlo very, very, very well, and I've also talked quite often with Abe Ashtekar. And quite a number of years ago, this might be 20 years ago or more, I said to them, do you think quantum gravity will require, first of all, to be, in the first place, a quantum theory of the whole universe, or only of a part of it? And both Abe and Carlo unhesitatingly said, no, we can start with quantum gravity in a part of the universe. We don't have to have a quantum theory of the whole universe. Now, with my Machian convictions that you have to talk about the whole universe, I disagreed on that one there. So that would be where I would disagree with Carlo and Abe. I think Lee has more sympathy. Lee is, of those three founders of loop quantum gravity, Lee is closer to my position, I think, than the other two.
Yeah, I agree. I think the thing that perplexes people and is sometimes used by proponents of intelligent design and proponent religious practitioners is to use this Borde-Guth-Vilenkin theorem and use it to basically motivate a beginning, which would then be in harmony with the Torah or Old Testament description in Genesis 1:1. Interestingly enough, that Fred Hoyle used to criticize cosmologists who support the Big Bang as being overly concerned with Genesis, which I think is laughable nowadays. People don't associate cosmologists with being fervent Bible beaters, but nevertheless, people do use this theorem. And Vilenkin himself says things that he doesn't actually believe it leads to a singularity, but he does say that the entropy, according to the behavior of entropy in the observable part of the universe, is many orders of magnitude lower than its maximum state. And the second law of thermodynamics says that the initial entropy of our co-moving region on this boundary, not the singularity, but the eventual boundary that all space-time geodesics terminate on, going backwards, must be lower still. So the universe must have originated in a very special, non-random state of extremely low entropy. In your mind, I mean, what is the lacuna, the gap, the problem with Vilenkin's claim, and that necessitates a new interpretation of time itself? In other words, armed with GR, armed with an expanding space-time, you don't even need to say it's inflation, although obviously Vilenkin and Guth are huge supporters of that. But nevertheless, if you just have an expanding space-time, you'll go back to some point in the past, and you'll achieve lower and lower entropy. And the question, of course, is that who ordered it to be zero in the beginning? But that's So I guess I'm asking, what are the failings of that theorem, the singularity theorem, which is a misnomer, of Borde-Guth and Vilenkin that your theory rectifies? Is it that it's purely geometric, it's scale free, it's gauge invariant? Is it that it's more an interpretation, a difference rather than an actual physical prediction? Obviously, they would predict inflationary gravitational waves because they support inflation, but you believe inflation is not necessarily mandatory. So what are the virtues of the approach that you've taken over theirs, succinctly as possible?
Well, I come back again. I'm going to get verging on religious now.
Okay, it's okay. We've had on rabbis and Christian scientists.
I I am very, very struck by this idea that the universe does have a beginning, but it's a very uniform beginning, and out of that then structure grows. Now, I recently checked out the etymology of the word creation. Do you know what it is, as a matter of interest?
Creation, the word in Latin, or
What is the etymology of creation? Well,
isn't it to emerge from, or something like that? To emerge.
You're quite close. It actually comes from an Indo-Germanic word, which means to grow. It's nothing to me. It's not creatio ex nihilo. It's to grow. Now, if you think about my idea that the universe starts very uniform, it's like a flat field with soil, just a little bit of variety in the soil. And then out of that, the grass and the bushes and the trees grow. And the quantity that measures that growth is, I come back to this extraordinary, in the Newtonian theory, in the point particle model, the quantity that measures that is this complexity. It does everything at once. It's the size of the universe, it's the intrinsic size of the universe measured by rods within it. It's the potential energy made scale invariant. I think there's a very good chance that it's time. So in fact, I would say time is creation, because the amount of creation is literally the time. It's the potential energy made scale invariant. It is really actually rather, if I may say so, an attractive theory. It'll be a pity if it's wrong.
Well, at least you're not saying what Einstein said on the occasion of the 1919 eclipse, saying that he would feel sorry for God if the data didn't bear him out.
Yeah.
I want to turn to a different epoch in the universe when it's matter dominated, far away from the radiation domination of the extremely early universe. Now it's matter dominated, and it's growing at a certain rate, but the rate of change is not accelerating yet because dark energy is subdominant. How does that fit in? How do you have periods of contraction or relative deceleration of rods and clocks in your model? How can that accommodate the observations that we know the universe was much less rapidly, differentially, relatively speaking to today, accelerating compared to what it is doing now and will do into the far future?
I'll be very speculative here and just suggest that perhaps the acceleration of the universe might be an artifact of not treating scale properly. All I will say is that, first of all, it's clear to me that clocks come into existence later on in the universe. It's quite interesting and very significant in the history of the universe is as it gets more clumped and matter gets more concentrated into galaxies and stars and things like that. And I think it's quite interesting that the acceleration seems to have set in more or less at the time, broadly speaking, when the universe really started to become significantly inhomogeneous. So maybe, I mean, Dirac and others conjectured that the gravitational constant was not constant. And in fact, when I was first collaborating with my Italian collaborator Bertotti back in the 70s, it was still experimentally an open question whether the gravitational constant was time-dependent, as Dirac had argued. Now that's been ruled out. However, I don't rule out a connection between the increasing clustering, the growth of black holes, the increasing number of black holes, with the rate of clocks, that these could somehow be, that could be some effect there, and that the apparent acceleration of the universe is an artifact of that. Now, that's very speculative, but I don't think it can be ruled out.
And when we look at the features of the Janus Point model, I think would be very interesting for me to get is your thoughts on the inspiration that you talked about from Leibniz is monadology. So how did you come up with this as an influence? What is the role that Leibniz plays in this, besides kind of being thought of as a counterweight, if I'm not mistaken, to Newton, who wrote the calculus as well as what Feynman, who plays a role in your book, he called the language that God speaks. So on the one hand, we have scale-free things. You're talking about gauge invariant objects like shapes being a primary fundamental monad of the universe, perhaps. But then you have calculus playing the actual role in differential geometry and relativity and so forth. So how do you reconcile these two aspects of mathematics and their usefulness in physics? And as Wigner said so unreasonably so, that on one hand, we need the calculus, which is inherently dimension full, but then these other objects are more fundamental in your estimation because they're dimensionless. So how do we reconcile Leibniz versus Einstein, or maybe even Euclid versus Newton as mathematical kind of protagonists set opposed to one another?
Well, you put quite a lot for me here.
Yeah.
Let me say there have been two, sort of philosophically speaking, there have been two huge influences in my life. The first was Ernst Mach when I read him. That was back in 1963. It wasn't until 1977, so 14 years later, that I read Leibniz for the first time. And just a few of his philosophical papers, and they made a huge impact on me. The thing that he said was that what he was really attacking was Newton's idea of space being something like a perfect translucent block of ice where there was no marks in it, nothing like that. And Leibniz just raised his hand in horror and says, if there's no variety in the world, we can't see anything, we can't begin without variety. So right at the heart of Leibniz's whole feeling is that we rely on variety, we rely on differences. And then his idea was that to have a world that is more perfect than any other one, it should be maximal variety, the variety. So in the monadology, he says that the universe is more, we live in a universe that is more varied than any other possible universe, but subject to the simplest possible laws. And I found that a very attractive idea. And Lee Smolin took it over very enthusiastically. And between us, we developed an idea called maximal variety, which still lives on. Now, interestingly, about 7 years ago, I had an introduction to the man who had just retired as the editor of the Leibniz papers. It's a colossal project. They got to volume 50 when I had lunch with him in Hanover. Mm-hmm. And he said, and I told him of my enthusiasm for that idea of Leibniz. And as I recall, he said to me, well, Leibniz actually had two ideas. One was that the universe is eternally more varied than any other possible universe. And the second one is that it's striving to become ever more varied.
We talked a lot about some of the novel concepts in the book. I wonder if you could just briefly recapitulate the two that are most significant to me are really in contrast to the so-called past hypothesis, which in essence inserts by fiat the low entropy state of the early universe. What is the replacement of such a phenomenon in the Janus Point concept?
The first thing to say is that the whole notion of entropy developed with thermodynamics out of the study of steam engines. And in a steam engine, the steam must stay in the cylinder, which is effectively in a box. And the main starting point I have to completely rethink the whole story of the entropy of the universe as opposed to systems within it. I mean, the laws of thermodynamics certainly hold in my kitchen where I'm sitting now, but do they apply unchanged to the whole universe, which I don't think is in a box. So that's my starting point to rethink the concept of entropy. So if I start with the simplest model I can, which is the Newtonian theory of point particles interacting through universal gravitation. And right back in 1772, the great mathematician Lagrange was studying the three-body problem, Earth, Sun, and Moon, and he found a very important result, which was, it was the first qualitative result in dynamics. It was, in the infinite past, as you think of it in Newtonian terms, the size of the system, that's its moment of inertia, is infinitely great. As time passes, it gets smaller and smaller. It comes down to a minimum value, a minimum finite value, and then it increases again to an infinite value. And I call that minimum point the Janus point. Now, if you have lots of particles at that Janus point, the system, the particles are more uniformly distributed than on either side of the Janus point. And in addition, as you go away from, and they're moving more or less like a swarm of bees in a random way. So you would say there that their entropy is maximal. It's very much like a lot of atoms in a box or a free gas in a box. But as you go away from the Janus point in both directions of time, the system breaks up into clusters and becomes much more ordered. And that degree of clustering can be measured precisely by a quantity, a scale invariant quantity. It's a pure number that I call the complexity, that defines direction of time, bidirectional arrows of time away from the Janus point. And rather than the universe getting more disordered as you go away from that disordered state at the Janus point, it gets ever more better ordered. Clusters formed, Kepler pairs form and go around each other in beautiful elliptical orbits. And so I would say this is an indication that we've got a completely different story when we think about the whole universe not being in a box, because it is just quite different. That Janus point is not there for some past hypothesis. It hasn't been nobody's had to add it to Newton's equations to put it there. It's there as a direct consequence of Newton's equations, as long as the energy is not negative. And even if it's negative, you'll get something like a Janus region in virtually all the solutions. So the main claim I make in the book, and I don't necessarily tie it to that specific Janus point model. As a second one where it's only half of that Janus point, so to speak, is that this just puts a really fundamental question over the whole idea that the arrow of time corresponds to the growth of an entropy of the whole universe, and that to explain it, you have to say that the universe started in a very special way.
And some of the notions that I've talked about on this channel have to do with not Popper's version of falsification, which I always point out. Popper actually thought that the steady state model or the quasi steady state model had some virtues, but actually the virtue of epistemological concision and austerity, parsimony, etc., but primarily not necessarily due to falsification, but nevertheless due to the ability for current day evidence to shed some light or some Bayesian confidence on our models. Are there predictions of the Janus Point paradigm that would lead us to have more faith in it? And is there anything that could falsify it? This notion of the fundamental nature of dimensionless objects and sort of gauge-free objects. Is there anything that could lead more evidence to it that exists currently or could exist in the future? Or is there anything that could prove it wrong, in your opinion?
I think there is real hope, and this relies on not taking that particular model that I showed where the size in the Newtonian picture remains finite, but it is actually zero. And now there are these so the basic idea that my collaborators and I have been following for some time is to use Newtonian theory to get some idea of what might be happening in general relativity at the Big Bang. Because remarkably in Newtonian theory, and it's been known for over a century, that there are situations in Newtonian theory, if you have a whole lot of particles that are interacting with Newtonian gravity, they can all collide instantaneously at their center of mass, at the common center of mass. And that's called a total collision. And by time reversal symmetry, you can reverse the direction, and then it becomes what I call a total explosion. And the very interesting thing about such a total explosion is that it has to start in a very, very special way. It has to start when the particles are in what is called a central configuration. The shape is very special. And there's one of those possible shapes which is extremely special, which is the most uniform state that the universe can possibly have. It's not exactly uniform, but it's very uniform indeed. And then as you go away from that total explosion, this quantity that I call complexity, the measure of the clustering, grows. In the classical theory, it fluctuates and it grows. And now, if something like this happens in general relativity, in a quantum form of general relativity, I think this could indicate that the universe of necessity, the law that governs the whole universe, starts in the most uniform way it possibly can, but with certain small fluctuations which then grow. And if you leave out all the fine details, this is broadly what we know about the universe. So I think there is a hope that if these ideas could be developed further in the context of general relativity, it would lead to precise predictions about fine details in the microwave background. And that would be a great triumph if it could be done.
We spoke earlier about the Borde-Guth-Vilenkin theorem and whether or not that could, be leading cosmologists to a low entropy state of the universe. What are your feelings about the Borde-Guth-Vilenkin theorem, which sometimes improperly is called a singularity theorem? As Vilenkin himself has said, it doesn't really predict a singularity. And as Sean Carroll has pointed out, there are alternatives to thinking about it. And perhaps the best way to think about it is when classical GR breaks down. One of the virtues of the Janus Point paradigm is that you only need Newtonian mechanics, essentially. It's very generative and classical general relativity. But I wonder, can you, steelman your opponents and say, what are the arguments that you believe are valid that motivate a quantum theory of gravity?
I think it's in the first place, I would say it's a quantum theory of the whole universe. That's what we need. I mean, certainly you and I couldn't be talking to each other if quantum mechanics wasn't governing the way things behave.
Right.
That's for absolutely sure. There's photons coming off my laptop screen showing your smiling face in California. That's an absolute miracle. So I do believe we need a quantum description of the whole universe. But the point I keep on making is that the idea that the universe has a size which is somehow measured by something outside the universe is just, for me, that stinks. I think it's just not tenable. If the universe is a self-contained object in Einstein's theory, if it's spatially closed, then any size it has must be some intrinsic size that's from measuring rods within it. And therefore, the only thing that one should look at is the shape of the universe. And I don't think anybody is thinking about that. Well, sometimes Roger Penrose is talking a little bit along those lines, but certainly not in the way that we are. So if you actually look at what the shape of the universe is doing, when you have these total explosions that start from a very uniform shape, this suggests a completely different way of thinking about cosmology. That the universe starts uniform. You don't need inflation to make it uniform because it must start uniform. That's the nature of the law of the universe. And it's a time asymmetric law. In this case, where we have a total explosion, it starts very uniform and it just goes on growing, getting more structured. The structures increase. And that matches exactly what we see. If you look through any telescope, that's the story the telescopes tell you.
And when we look back in cosmic history, we see after an early period, very brief period of radiation domination, the universe became matter dominated. And there it stood until, 5 billion years ago or so, when it started to accelerate. How does entropy behave, and how does the Janus point reconcile the relative deceleration of the universe, if not a contraction, still the arrow of time and so forth? How does that behave in a universe with multiple components, just taking matter and dark energy, which we know to exist? How is that reconciled with the Janus point paradigm?
Well, let me say I'll have to call it's the half Janus point paradigm, where
yes.
The theory starting with a total explosion in the Newtonian, in the standard picture with size, it's where the size is zero. But I would say size is a gauge degree of freedom. That what you should think of is the universe starts in the most uniform shape it can possibly have. Now, rods and clocks don't exist anywhere near the Big Bang. They come into existence later on as the universe evolves. If the universe is all tightly interconnected as a Machian relational picture of the universe says it should be, then I think it's quite possible that the accelerated expansion of the universe is actually not really there. It's because we don't realize that the rates of clocks are affected by how clustered the universe is. And it is interesting that the accelerated expansion seems to have begun more or less at the epoch when the universe was becoming significantly clustered, clumpy, inhomogeneous. So that's a very tentative idea, but I think it's not impossible. We do know that Dirac thought that the gravitational constant was time dependent. Now we know that's ruled out. But I think it could be that there's an overall effect of it's our not understanding the way clocks work, and also, I mean, I do think there must be a quantum description of the universe, but the rules of quantum mechanics that we find about us, I believe, are emergent. So they don't, the universe, the quantum mechanics of the universe doesn't look like the quantum mechanics of the objects, the things we study in the universe, in the laboratory. And that is matched with the origin of inertial frames of reference. Ernst Mach said, the law of inertia, the inertial frames of reference, they don't hold in bland absolute space and time as Newton imagined, sort of a translucent block of ice and a clock ticking away, independently of anything that's happening in the universe. Mach said somehow or other the fact that the law of inertia is something due to the action of all the masses of the universe on each individual body. And that is the theory that I elaborated with my Italian collaborator Bruno Bertotti back in the late 70s, early 80s. And I think that is the definitive implementation of Mach's principle, Mach's idea. And I think it's entirely possible that something happens with quantum mechanics, that the local quantum mechanics we see with Hilbert space and operators and all that is an emergent effect from a rather different quantum mechanics of the entire universe.
I see. And I think the last kind of topic that I want to get into is this very provocative statement that you made that position is fundamental, but momentum isn't. And I wonder if you can answer that in just 1 second. I want to remind people we're talking to Julian Barbour, a renowned cosmologist, a true remote mentor to me and many people. I'm sorry to tell you, Julian, you have influenced me to the good, hopefully. So I'm going to ask you about the primacy of space over time in just a second.
Yeah, you've got to call a stop at some stage. Yes.
I could talk to you for money. I could talk to you till the end of time, which could be a long period of time. So Julian, now what I would love to do with you, if you will indulge me, is go into the impossible. This is when I ask my guests to honor me by coming on this podcast with kind of the big picture topics. We discussed a lot about your knowledge, which is the word science in Latin. Scientia means knowledge. But now I want to talk to you about your wisdom, your sapienza. And if we could do that, it would be quite a great thrill to me. So would you mind talking about the so-called big picture questions that I always love to ask my guests now in the Into the Impossible segment?
Yeah, that's fine by me. Yes, I'll do my best.
Okay, here we go. So the first one has to do with sort of a concept in Judaism or in the philosophy of my religion, which has to do with what's known as an ethical will. So many decades from now, when you reach the biblical age of 120 years old, and as Shakespeare said, and you quote many times from Shakespeare in this wonderful book, The Janus Point, you depart again, not for 50 years, please, God or nature or Janus, if you will. I want to ask you, what do you want to put in your ethical will, not your knowledge, but your wisdom to leave for future heirs of the ideological kind, which I count myself as one.
Yeah, well, I did. Let me just. I did make just a few notes because it's quite a challenge.
Yes.
So first of all, when I was in my late teens, I got very enthusiastic about antiquity and above all the Greek authors, and I picked up from them two Greek sayings: "In all things moderation," and "Know thyself." Know thyself is at the oracle at Delphi. And certainly, I think I've certainly done, I think, quite well in all things moderation. I never smoked, I never drank excessively and things like that. I had one
of us.
And so forth. Know thyself is harder. I'm not sure quite how well I knew myself. Perhaps I could say that I used to be, not terribly seriously, I used to be bipolar and didn't know about it. You didn't read about those things when I had it. But by great good luck, I was put on medication back in 2004 after I had been psychotic, which has completely eliminated all traces of me being bipolar. You might not have thought it at times in my thing, but it's a miracle. It's the medication they used to give to epileptics called valproate. They don't understand why it works for epilepsy. It's an anticonvulsant, but it has definitely stabilized me. Once I went on to it through a trial, I joined a trial, and it cured me. So now I think I can say I more or less know myself. So the other thing that I did, I was very lucky in going independent. And I think I was lucky in my father. He'd been an independent Arabic scholar. He actually became deputy head of the Arabic service of the BBC. And he may have been a bit of a role model for me. So I would say, don't be afraid of going independent. When I got really interested in the nature of time and motion, I decided not to go into academia. I decided to go independent. Felix Birani, a noted relativist, I asked him what it's like being in academia. He said, if you can do the administration, give the lectures, and write 1 or 2 good research papers a year, yes. If you have doubts about any of those 3, no. And it was clear to me it wasn't for me, because I wanted to study the nature of time and motion, and there was no way I was going to produce 1 or 2 good research papers a year. So I went independent, and I deliberately took up the most boring job imaginable, which was translating Russian scientific journals into English. I got into it by chance. I'd learned Russian as a hobby. And would you believe it, for 28 years, I translated those journals. But it gave me a salary at least as good as a professor, and I had 1/3 of my time to do exactly what I wanted.
Wow.
And I reckon an interesting thing is, I reckon I generated about 70 million words in English. Now, and those are all on library shelves around the world. Now, if you ranked humanity in order of how many words they generated which are on library shelves, where would I come? I think I've got a sporting chance to be in the top 20.
I think you do. Yeah, I think you do.
It was desperately boring. But I opted for that against trying to set up because a lot of people say they'll make a business, make their fortune, and retire at 35. And I said to myself, if I try that, it won't. I'll get so hooked by the business. Better to have a boring job where I'm desperate to get away from it and think about the physics. And it worked. And then in 1996, on the 19th of May, I said, I'm not translating anymore. AndVe been free now for 25 years. And I've had 25 years with really good collaborators, top-class collaborators. And the ideas are still coming. They're great. And I'll say one more thing, there's a wonderful stand-up comedian, Paul Merton, in this country. And he published his autobiography a few years ago, and I heard him interviewed on radio, because when I decided to go independent, my family and my wife's family from Germany said, you're taking a huge risk, Julian. And Paul Merton decided to become a stand-up comedian when he was 16. And in the interview on the radio, he was asked, didn't that feel risky? And Paul said, it didn't feel risky, it felt necessary. And I suddenly realized that was exactly what had happened with me. So my ethical will would be, if you really feel something is necessary, perhaps have the courage to go for it. And certainly I've never regretted it. So then one other thing I will say, you asked what was the best job I had? Somewhere the best job I had, for 4.5 months, I was a weather observer in the Canadian Arctic. By some chance, I got a job just a 1/4 mile inside the Arctic Circle at Bathurst Inlet It's one of the beauty spots in the Arctic. I was there for 4.5 months, and all I had to do every 3 hours, I had to do 5 minutes work, which was make a weather observation.
Well, at least there's consistency there. It's like San Diego, you know, it's very easy.
I absolutely loved it there. I mean, there were about a dozen Inuit. There was a Hudson Bay company, a man with a Hudson Bay, and just one Canadian I was with. And I took 2 suitcases full of books and read them by the midnight sun. And for years afterwards, I would say, I've got to go back to the Arctic. It was so beautiful. But amazingly, and this is the thing which I do think we should really try and preserve the world. It is so amazing. And the worry of wars and climate change. So far as I know, the average temperature at Bathurst Inlet, where I was for the summer of 1958, is now 4 or 5 degrees centigrade warmer.
Wow.
Yeah.
Yeah.
That is just staggering. You know, when I've gone from early 20s now to 84, that is a scary thought.
Yeah.
So that brings me on to what I would say is, you know, yes, you asked me about, I mean, you suggested I read at the end of Genesis, but I'm very impressed by another Jew, that is Jesus, and he summed up it in 2 commandments. Love the Lord thy God with all thy heart and with all thy soul and with all thy mind. This is the first and great commandment. And the second is like unto it. Thou shalt love thy neighbor as thyself. Of these 2 commandments hang all the law and the prophets. Now, I'm agnostic. I've no idea where the universe comes from, why I'm here. But I do think it is precious. And, you know, I think it would be an appalling tragedy if intelligent life disappears from the universe. We might be the only place in the universe where it exists. So I think that's very important. And I do think the preservation of intelligent life and happiness are valuable. So I rate happiness very highly. So as regards Jesus' second commandment, I accept it totally. I say, try to treat your neighbor as yourself, but make sure that you're happy yourself. Otherwise, you're just going to be a downright miserable person.
Right. And that's
other people. And I will say of myself, luckily, I've basically been a pretty happy person. I've been blessed with a cheerful personality, it seems.
Yes, you certainly have. And you are very influential on me and literally thousands around the world. Yes, it is true that the commandments are very, to be taken seriously, means that if you have to love your neighbor as yourself, you know, all the more so, we say in Hebrew, kol v'chomer, do you have to love yourself like yourself? But you know, if you have to treat people with weightiness, with importance as your parents, and so you should treat yourself. And that's great that you mentioned self-care and taking care of your mental health as you did. And I imagine that will play into your advice to your former self, which will be the final question. The second question, though, is reminiscent of one of the characters in this book, Richard Feynman, who has many appearances in the Janus Point. And he said, if asked to summarize the greatest amount of information in the shortest sentence, he said that he would sort of put forth the atomic hypothesis, that everything is made of atoms and they have electrons and structure and so forth. I want to ask you, if you had a monolith, a time capsule like Arthur C. Clarke's Sentinel, and you could be guaranteed, Julian, it would last for 1 billion years, what would you put on it or in it besides a Northern Canadian weather forecast?
I would put my 2 triangles.
Yes, let me see them. Hold them up.
So here they are. Now, the fundamental question that goes back to Newton and Leibniz is, how do you define motion? What is motion? So Newton invented absolute space and time so that he could give a mathematical definition of the law of inertia. So for him, there is an absolute space like a block of ice, and in it you can draw lines and free particles will move in a straight line. And Leibniz said this is nonsense. All that happens is there are separations between particles and they change. So if at this triangle, at the vertices of the triangle, there are three particles, they can move, according to Newton, they can move in two ways. They can change the separations between the particles, and at the same time, the whole triangle can be moving in absolute space. And Leibniz says, no, that's no good. All that is real is the changes in the separations. Now, I do take very seriously the principle of least action. How do you define action? What is the action when I go from a triangle that has this size and shape and a triangle that has that size and shape slightly different? And I'm going to say what is the difference between those two triangles without using the position that they are in my kitchen. I'm just going to use the two triangles. So I'm going to say, I take this as my reference triangle, and then I take the second triangle and I lay it on top of the other one and try and bring it to overlap, to congruence. Congruence is the fundamental principle for making proofs in geometry. So I'm going to try and bring it to congruence, but I can't do it exactly because they're not the same size and shape. But what I can do is move them into different positions, and then I can take the separation where particle one is in this triangle and in this triangle. So there's a separation. I'm going to square that separation. I'm going to multiply it by the mass of that particle. I'm going to do it at each of those three vertices. And then I'm going to add that up, and then I'm going to move it until I get it into the position that minimizes that quantity. And I say that that is the process of best matching. That was what my collaborator Bertotti and I developed in our paper published in the Proceedings of the Royal Society in 1982. And I think I am very confident that that actually solves the problem of how you define motion, provided the universe is a self-contained thing. So that's what's going to go in my monolith out in there. And there's quite a nice, I used to travel to all the conferences with my triangles. They were two big cardboard, plywood triangles, and hold them up and do that. And on Google Images, you can find a nice color picture of me in Krakow in Poland doing it. So
yes, we'll include that.
That's my monolith
in the background.
And I do feel, as long as the universe is something self-contained, I'm very confident about that, because it meets a lot of criteria.
Maybe what we'll do is make your monolith have a triangular cross-section, or multiple triangular cross sections, like some kind of Penrose staircase. And the final question that we ask all of our guests has to do with Sir Arthur C. Clarke's third law. Did you ever know Sir Arthur, Julian?
No, I've read one or two of his books. When I was younger, I did read a bit of science fiction, The War of the Worlds and things like that. But I don't read any science fiction now. But yeah, I certainly know of the man, and he was a great writer, that's for sure. Yes. So
he had many great aphorisms, including my favorite from time to time to use with my colleagues is he would say, for every expert, there's an equal and opposite expert. But for now, his third law gave me the name of this podcast. His third law states the only way of discovering the limits of the possible is to venture a little way past them into the impossible. So I want to ask you, what was the aspect of life that was most mysterious or most foreboding, intimidating as a 20-year-old, but now makes perfect sense to you because you had the courage to go into the impossible?
What worried me? I tell you what, I don't think I was ever seriously worried by anything, Brian. Well, I was dead lucky. I mean, my father was earning good money at the BBC. He'd inherited some money. I was very lucky. I had a very stable upbringing. At school, I could high jump. I was reasonably athletic. Now you ask me, I don't think I ever worried about anything. I wanted to become an astronomer. I got absolutely hooked on astronomy at about the age of 10. And until I started asking myself, what is time and what is motion, I still wanted to be an astrophysicist like you, or a cosmologist.
Mm-hmm.
But then suddenly these questions came. So I said, I'm just going to try and answer these questions. I was lucky. I wasn't. Is that a satisfactory answer?
Yeah, you knew early on. Well, that's great. And you also gave wonderful advice earlier in this segment. But Julian, for now, I want to thank you for having the courage, the brilliance, the insight to go 2 hours plus with me in total. And I think, again, this could be just the logarithm or the of the amount of time I wish I could spend with you. And I hope I get to meet you someday soon.
All right, great. Good to talk to you, Brian. Thanks very much.
Any sufficiently advanced technology is indistinguishable from magic.